Happy post GTC to everyone. This is our 101st lecture. I'm, thrilled to have Kapil, who's been like one of our most like recurring lecturers so far, who's here to talk to us about learning Cutlass the hard way. So Cutlass is hard. I'd expected a title like "Learn Cutlass the Easy Way," but perhaps I think this is the only way to actually properly learn it. So, Kapil, it's an honor to have you back. Please take it from here.
Yeah, thanks, Mark. Yeah, I'm always fun to come back. Yeah, so yeah, this was, I mean, where GTC says this. I worked on sort of like learning gems properly like a few months ago. I think this was like probably around PTC, before PTC, because I was like, oh, I need to get ready for like PTC properly. It's like, because there's going to be a bunch of people talking about a bunch of cool stuff. So I think they're just getting up to speed on like the like essentially like latest hardware primitives and make sure like I'm able to like get the most out of the um, out of Triton conference and PTC, essentially, which just went down this path. So the the main I feel like it started from like when I was reading some of the blog posts from other folks. I think this is in the same realm of post that like I think Simon Boehm wrote like a couple of years ago on like going through essentially bunch of optimizations on gems on A100. Then Alexa had a post like last year, essentially similar, like going through like hardware details of Hopper. And I believe Pranjal gave a similar presentation, I think about a year ago, on like when he went to like the Hopper optimization. And I've seen a couple of other similar ones. So like yeah, I think like it would be good to explore it, but it was sort of on my own time. I didn't have an access to like an A100 or H100 on my in my personal lab, so I was like, okay, let me just try to sort of test it out on a 4090. So that's where it's basically started. So took me about a month to sort of go through some of these blog posts and sort of build my own intuition about these things. But essentially, like over about a month and a half, like I wrote a bunch of kernels. Back then like Claude wasn't as good at writing kernels, so it was sort of like still early stages back then. It was useful, but not beyond just sort of basic like code blocks. So I feel like it was like still fairly artisanal code, like 6 or 7 months ago. But essentially like fairly helpful for me to get to like the understanding of like why we needed Cutlass, to essentially up level some of the hardware level primitives in software, so you can write sort of most optimal gems as we move from like MPay to Hopper to Blackwells. So I don't have a lot of experience writing gems on Blackwells, and honestly, I don't have a lot of experience writing gems in general. But this was sort of my way of just hacking and understanding this. Uh, I mean, a little bit about me. Like I've been on GPU mode before. I work on the PyTorch team at Peta, and essentially, yeah, love all sort of GPU fun stuff. I currently work on distributed primarily, and essentially, like I wrote two pad blog posts. Like one was mostly on RTS 4090, and the other one was on H100. And essentially like we'll just go through like the blog post one. Blog post two, I would try to cover like the main concepts that were useful to sort of understand like iterating on Cutlass. Like I won't try to get too deep into the weeds on the optimizations, but I think like it's really good to just understand like what are the sort of the conceptual underpinnings which sort of define how you write like optimal gems. I mean, for example, like when somebody says like, oh, we are iterating on a TMA warp specialized ping pong schedule, like what the hell does that mean exactly? Right. So I mean, that's literally a class in Cutlass. That's essentially like. But anyway, I think like so. Let's dig into it. I'll sort of just go through my blocks, and like let's start with block number one. Uh, I don't know, Mark. Can you switch to the block now, if possible?
Yes, 1 second. Yes.
Awesome, thank you. So yeah, I mean, So I sort of gave a little bit of premise already, but essentially like this, literally like this. Most of the work that I did here was primarily just sort of inspired by some of the awesome work that other folks have done already. So I think like I would recommend going to some of these blog posts as well, which are already linked there. Uh, but if we go through the blog post, I think there's a bunch of basic stuff here as well. I think like I'm gonna sort of skip past some of these because I feel a lot of this was done during the early days of GPU mode, back when it was called CUDA mode. I think like going through the PMPP lectures will sort of get you to at least I believe like 2D block tiling, if I'm not mistaken, or at least like the at least up until the shared memory caching, like the first 5 to 6 chapters. But I think after that, things get more interesting as we sort of move into like the Cutlass land. Um, so I guess like yeah. So on the basics front, so like I mean, it's essentially like the most naive way of like writing the kernel is essentially like you're doing a like essentially element by element multiply and just accumulate every single value one at a time. It's like the most inefficient way of writing a gem kernel. And I guess like I should have said earlier, like what I found Claude really useful for was like creating these JavaScript visualizations, which were actually very useful once you get to sort of the more complex like tiling strategies. But yeah, essentially like but and I guess like the next thing is you can essentially like uh, uh, improve on that pretty quickly by essentially just switching the way you iterate on these element by element. So essentially, you can change it pretty much to you going through matrix A, like row by row. So essentially, you can get to global coalesce memory loads. So then essentially that gives you essentially some improvement pretty quickly. And this was also sort of like some of these initial things were already sort of done by Simon Bourne in his blog post as well. Um, so you can see like here, we started with like very bad performance. We pretty much got like a big boost just from just changing the order in which how you iterate. Uh, um, Now, sort of quickly going to the shared memory caching, which has been covered before, but just sort of uh, uh, just to go to some of the basics early, like you can what you can do next is instead of loading data directly from global memory, you can actually like create a shared memory cache, and essentially you can move blocks of data into the shared memory and then iterate and essentially do again the same point by point uh, uh, matrix multiply add. Um, Now, essentially, like what like what some of the conceptual things that are useful to understand as we get here is essentially like how do we schedule sort of schedule these on the GPU. So essentially, like as I think, like most of the folks who are like part of this community are fairly aware of like how essentially threads get divided into work. So you essentially are scheduling all of your work over as SIMT over what like of 32 threads. So essentially, like the next thing to think about is essentially like how can we get a better occupancy on the GPU. I do cover some basics of occupancy here, and I think if folks are more interested, they can actually look at like Modal's GPU glossary, which actually goes into much more detail on like what essentially occupancy is. But the main idea is essentially you would want your SMs to be always be busy and essentially making sure that we having them computing stuff all the time. And essentially, like initially we started with like let's look at the kernel here. I believe we started with 1024. What that essentially means, essentially, you uh, you get to a lower occupancy on in terms of your one in India, you get to around like 67% of like occupancy on your GPU. But to get to like slightly higher, you can essentially like split up your work into like smaller blocks. So your SMs are busy working on like smaller block sizes, uh, and essentially like now and I guess the NCU is fairly useful there as well. You can get all of these numbers directly, but you can actually like hand calculate them as well if you're curious. Um, but essentially, then the next optimization that we would want to do is essentially we move the data to shared memory, and like how can we get a better register utilization? Like you would want to essentially like have data cached locally as much as possible, so that like we can actually like uh, or taking a step back, you would want your SMs to be doing compute most of the time, or like or have them uh, more more compute intensive work would always be better for us to like improve the arithmetic intensity. Um, so the next idea here is essentially like originally we let me actually go to the visualization, which will make it clearer. So essentially. So originally, this is what we were doing. We were essentially going through each one of the values and calculating them point by point. But what we can do is essentially, originally each thread was essentially operating on each one of these computes. But what we can do is that we can actually take a thread and have it do more work. So which is essentially like where the first level of thread tiling comes in. So you can take one of the elements of B and cache it, and essentially like now operate four at a time. So essentially you just like 4xing the work that each thread needs to do, so that we can just get more work per thread. So I mean, just to show this again, essentially like here we're just caching B temp, which is part of tile B here, and uh, and I guess like at this point, I also realized like Simon's kernels, when I was trying to sort of replicate them, they didn't do like bounds checking, and I was actually like iterating on like a lot of different kernel sizes initially. So it wasn't working correctly for some of the non 2 powers of 2 kernels. So, but yeah, that's an aside. But essentially, like at this point, I was starting to learn that the indexing in the it becomes really hard as you're starting to sort of go from a basic shared memory caching kernel to start adding like your thread level tiles in there. So I mean, this is the full listing. So essentially, like we we load the data here. Then essentially for per thread, we cache one of the values and essentially like operate like 4 values at a time. Essentially, as I showed earlier as an example. Uh, um, and if you see through the listings, most of these listings are essentially just exposed through to the Python dispatcher, so you can just call it directly from Python, because that's how I essentially like benchmarked most of these kernels. Like I had a PyTorch kernel, and then I would basically have like the PyTorch dispatcher just like load in the custom Cutlass kernel, which I think that some of the other blog posts actually had, like they were essentially just doing like sort of C++ based benchmarks, etc. I just found it like slightly higher level and easier to iterate on. But essentially, like just from adding like one level of thread tiling, where you can essentially like increase the arithmetic intensity of your kernels, you get a pretty good benefit from there. So essentially, like this is so the orange one is like the 1D block tiling, and then you pretty much go from like 5% to about 20% of like the Cutlass performance. Um, Now moving on, you can essentially just extend. Like I do cover like some of the essentially like you can essentially like at each level. Like I was also looking at like the NCU profile to like get a better sense of like what sort of like what sort of optimization suggestions that it would give. And I think like that is a good way to at least like and I think this is sort of repetitive advice, but I feel like it's fairly useful. Like you write a kernel, you like run it through NCU, and it will just give you like nice optimization advice in literally in the summary page. So for example, like here it's saying like we actually like reduce our thread occupancy, but the idea was essentially we increase the arithmetic intensity. Uh, Now essentially the natural extension of like the 1D thread tiling is to essentially now you can do even more work per thread and essentially expand it to a 2D tile. Now the idea is essentially now you cache along both of the tiles. So you essentially like as you're calculating your tile wise matrix multiply add, you can essentially cache values from each dimension in your thread tiles. So in the m dimension and in the n dimension. So we essentially just naturally extended from like a single value to essentially like an array of values. Uh, and I guess the basics are the same, and then you essentially just like first 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 cache the values in your registers, and essentially like then your accumulation is essentially just over the actual register caches, and you just accumulate over it in the k dimension. Um, so yeah, this visualization should essentially like make things even more clearer. So essentially like when you think about like when you go from like 1D block tiling to 2D block tiling, your final matrix multiply operations, essentially the the compute that you're doing essentially just becomes an outer product over each individual slice. So essentially like all you're doing is you're um, taking the outer products and accumulating them over multiple iterations essentially. um, so at this point so as we go from like 1D to 2D block tiling, it actually gets us to like uh, seems like around 30% of the Cutlass performance. Like we started at less than 1%. I think like now it's already up to 30%. But at this point, I mean, I think like it was getting clearer to me essentially like the how though I had heard about it like oh like the memory hierarchy is so important. Like we need to make sure that we are able to like feed the data to the GPUs as fast as possible so we can do more compute. But essentially like for most of this we haven't really changed the algorithm much. Like all we've done is essentially just try to put more put more work on each thread and just like work over the same amount of data, but essentially just utilize more of the compute as much as possible. um, uh, Going from here, essentially like the next level of optimization, essentially like now originally if you originally we were essentially when we were copying the data from the global memory to shared memory, we were essentially like taking it like one element at a time, and most of this was originally like for FP32. So essentially like we're taking each value from global memory. I can just literally go to the code listing. I think that might be useful. uh, so I believe this, yeah, essentially here. So you're taking like values from the global memory and essentially putting them in each individual tiles one at a time. So, but uh, uh, but what we can essentially like we can actually improve on this. So essentially the idea is like Qt actually provides us with like vectorized loads, so we can actually load multiple of these like float 32 values at a time. So essentially you can just like uh, you can reduce the you can for the same amount of time you can essentially like get like 4x the amount of data. So essentially like these for example like float 4 loads will have like you can load 128 bits at a time. So essentially you get 4 individual FP32 values at a time. So and the code is fairly simple. You can essentially like you can take your uh, original global memory and essentially like take chunks of 4FP32 values and just like copy them over using a reinterpret class over. Like so here, for example. Um, and essentially like what you will probably see is like if you look through your NCU profile is like your load instructions will actually change from like I, I I think it was like LDGE to like LDGE 128, which essentially like you'll take like 4 elements at a time. So you essentially like you the idea is you just like you 1/4 the number of instructions you need to load the data into your tiles. Um, and essentially, like once you do that, what you're doing is essentially just trying to feed the data to the compute as fast as possible, or like you feed the data to the compute faster, so uh, gets you slightly more bump in the performance. Instead of focusing on the compute this time, we just focused on essentially the data nodes. Uh, so we were originally 35, we're now approaching around like 40% of the performance. Uh, now the I believe this is where like the original post from Simon ended, or like it could be like he did cover warp tiling, but I'm not fully sure. But essentially, like the idea was like at this point I was starting to get the hang of it, and then I started reading through some of the like linked NVIDIA blogs, and like you can essentially like, just extend the idea of like you're taking your data from your global memory to your shared memory to your registers to essentially add another layer in between because we essentially know all all the work essentially happens at the warp level. So you can introduce this idea of a warp tile. So essentially, like now, what you're doing is essentially instead of iterating over all the threads, you will split them over essentially like warps of 32 threads essentially. Um, and I think we're slowly sort of approaching the Cutlass land, but this is essentially like, one of the visualizations from the original Cutlass blog, if I'm not mistaken, like the Cutlass during Cutlass 1, Cutlass 2 time. Uh, but essentially, like let me go to the visualization. So if you can see like originally we were doing an outer product over like uh, essentially like a single thread tile, and in the n dimension a single thread tile on in the n dimension. Now we can split it up across warps. So this is like a hypothetical example where I just split it into like chunks of 4 and 4, or you can think of it as like essentially you can have 32 threads along a single warp along the m dimension and the n dimension essentially. Um, and the final result is essentially the same. Like you're still doing you still essentially accumulating the final output over the same n cross n output tile, but you just like split it along the warps. Um, so so at this point, I think like I started looking into like Cutlass a little bit more, but essentially like let's quickly look at the results from like when we actually split it up by warp tiling. We actually get a little bit more of a performance boost. Um, at this point, I was starting to realize though like the indexing math just gets really crazy. Like for example, if you want to look at the actual listing, uh, this is the state of the kernel now. So uh, you essentially do your tile loads here, and it then you search. Then, for example, here you're uh, loading them into your register M, register N, and then you're essentially going over your warp level iterator and your thread level iterator. So you essentially have this like multiple nested for loops. And I believe like I think like there have been like few really good talks on Cutlass Qt previously, and people have I think like Chris Checker and Vijay and like others have shown those like giant loops of like 6 level nesting of like these like indices and like why like Cutlass and Qt sort of came about from like all of the shenanigans that you need to do with like the indexing math here. Uh, um, like for what it's worth though, like with LLMs, like you can actually track down these things much easier. But I think if you were to do this like artisanally back in the day, like I would like it, this would be really really hard. So now so far, so far, like we've been operating on FP32. So essentially, like we got to around 50% of the performance, but essentially, like the main idea is like I think since like Volta, I believe Volta or the was the first one with Tensor cores, but I forget. But essentially, like we want to be utilizing our Tensor cores, and we haven't done anything in that regard. So essentially, like this is where I think I forked off of. Some of the older block codes. So essentially, like they operated primarily on the FP32. So like now, like to utilize Tensor cores, you have to start sort of thinking about like how can you replace some of your indexing math that you already have with actually like Tensor core instructions. The first thing I found was like there's like some of the older WMMA API, so I started sort of iterating on that. So and to operate on Tensor cores, you have to be in sort of the BF16 FP16 world. So I started originally with like the before I got to Cutlass to like how can I like up level some of the indexing math and replace them with WMMA's API. So let's jump to that. Actually, before we jump there, so I did try to like take the existing kernel that we have and essentially just change the data type and get like what would be the actual performance on the FP16 BF16, and it was like really really bad. So it's like so you can think you can theoretically double the T flops. Now with and you can see like originally we were around 80. Now with FP16, I believe I did like BF16 as well, but theoretically they should be around the same, like 160 on RTX 4090, and we were like around 1/4 of the original. Whereas like with FP32, we were starting to approach at least around 50-55%. So now this is where Tensor cores come in. So essentially, like the idea is like if you think about your thread level, thread tile level, like outer products, you can essentially like replace those with Tensor core instruction. So this gives a good visualization from like one of the old NVIDIA posts. You essentially just like Tensor cores will just essentially up level that whole computation as a single instruction. Um, and essentially like there are like multiple different ops, so you can or essentially instructions, so you can think of like here like I actually like provide an explanation. So essentially like if you're looking at this instruction, or actually like let's look at this one. For example, this is one of the Tensor core instructions, I believe on Ada, or I guess Ampere and Ada are same. But essentially like your output is so you're doing an MMA. So your M tile is 16, L is 8, K is 8. So K is your reduction dimension, M is your row dimension, N is your column dimension. Your output is at FP32. Your inputs are FP16, and then accumulation is happening over like FP32. So essentially, like when you're doing FP16 computation, you would still want to do the accumulation in FP32 for better numerics.
So, Kapil, we actually
Yeah.
have Chris Seka in chat making a bunch of comments, so let me just read through them.
Awesome.
So the first one is he's saying that LLMs are terrible at raw indexing, and that tends to be the first thing that breaks. I think that was like a previous comment around 9:30. But more recently, he said, not using tensor cores is not the primary limiter in these raw kernels. The raw indexing, naked implemented, is fine, but in these implementations, the raw indexing is performed with dynamic thread index.x indices. So first, you want to remove all dynamic indexing from the innermost loops.
I see. Okay. Yeah, I mean, I like, for me, like, it's like I'm like when I started this, like I was like a fairly noob in this world, but I think that's useful to know. So even for like
Exactly.
FP16 and BF16, like you can essentially like get uh, like tensor core level performance through, or like I guess you want them to be static. Is the idea? Am I getting that right? I see. Okay, okay, that makes sense. Yeah, that makes sense. Um, so essentially, so on my like consumer grade GPU, like the main instruction that I basically focused on was like the essentially your SM80 1688, and you can get this instruction like what instruction you would want to get your kernel to use. Like you can essentially like use your standard PyTorch kernel, run it through NCU, and you can get like essentially like, oh, if you're not using the right instruction, you can essentially get your kernel to get to that. Essentially, that should give you essentially like idea on like what are your tile dimensions. Um, Now, like at this point, I basically, as I said, like I was using the older WMMA API. I don't know like how much people use this anymore, but essentially like I replace some portions of the code to like directly use the WMME fragment. So essentially, you can pull some of the load side of the kernel and the MMAs part of the kernel. You can replace them directly with like the API that WMMA provided directly. So which actually made my code a little bit simpler to understand, and essentially like that sort of gave me some level of like abstraction that I can think about when I'm thinking about like going from sort of uh, like going from like the global memory to shared memory to like the word tiles to like the final tensor core instruction essentially. Um, uh, and at this point, essentially, the performance that I got was like slightly better, and I'm assuming like some of this has to do with like the way I was doing my like baseline kernel, like with like all of my handcrafted indexing logic, and WMA just abstracting that away like helped a little bit, and I'm assuming it's doing some optimization under the hood. Uh, but essentially like still like I wasn't satisfied with the results at this point. um, but essentially like the at this point I was essentially like learned about, okay, like there was there's like a long list of like blog posts from like Nvidia. So like if you're like starting from scratch, I think it's like really good to just like go through some of the older ones. So like then I found one which was around like double buffering. So uh, but like at this point I was like the mental model that I was starting to develop was like is essentially like the idea that you get the data to your computer as fast as possible. And so far, we've been sort of doing it like sort of synchronously. But as you sort of think about it from like the later the later generation like Hopper, Blackwell, etc., uh, it really comes down to like you take your traditional distributed system concept and just like lower them all the way down to hardware. The reason why I say that it's like double buffering is essentially like when I first look at it, it was like, oh, this looks like a simple, like circular buffer, like just like, but like you just shrink it down to two. Um, but really like this is where like things started to click for me. Like so like what you do is like now so far what we've been doing is like we load the data, we do the compute, we store the data, and like rinse and repeat. um, but what you would want to do is like you would want to like have your GPU be busy doing compute while you're actually loading and storing the data essentially. So the simplest way to do that essentially like is what double buffering is. So now uh, so like let's talk to this. So essentially what we do is like originally we had like a single tile for A and one tile for B. What we essentially do is we just like double the amount of about tile memory. And we sort of ping pong through like the read tile and the write tile. So what we can do is like we can load the data into one tile while we're computing on the other. So essentially, like so what that looks like is you can essentially like toggle read and write through these buffers. So um, I hope that that sort of makes sense. Like, but essentially the idea is you just like load the data, run the compute. But while you're computing, you can load the data for the next compute in the next buffer, and then you just toggle in the next compute, and then you just go back to the index zero and like go back and forth essentially. And essentially like this is where I started to sort of understand like what like the gem pipelining is about. Like uh, uh, so I've done like some distributed system work back in the day, but essentially like and like high frequency trading, for example, like it is very you we try to always avoid, for example, like queues which were like dynamically allocated. So we always use like statically allocated buffers, which were your queues. So essentially like you can extend this idea of like double buffering to like n buffering, and you can essentially like uh, uh, you can load data into like some number of buffers, and you can compute data on some number of buffers, and essentially like that's where the concept of like the pipelining stages can sort of come about. uh, but uh, but I was sort of thinking about it like in my head, but essentially like once I started iterating on Cutlass later, like it became more apparent, because Cutlass has an actual abstraction for this like number of stages, for example. um, but at this point, like it was like, man, this is hard. Like let's just like let me see. I think I get it. Cutlass is useful, so let me just try to see like what a basic Cutlass kernel looks like. So this is where like the title of the blog post sort of came about from the fact that like I was going through all of this like painful process to get to like, okay, like just write a simple Cutlass kernel, because like it just basically abstracts away all of this like painful work that you have to do, just in sort of simple parameters. Um, so let's get to that. So essentially, like now the idea is like and this is like old Cutlass 2.0. So I have like the next blog post I did was like Cutlass 3 plus, which has a different API, but we can get to that later. But the idea is like you specify all of your tile shapes ahead of time as these essentially your static templates in Cutlass, and you pretty much take you give it like essentially your d types, etc., and then your the architecture, and it will do all of the hard work of like the indexing math and everything in the background. And when we think about sort of the accumulation part of the of our gems, it essentially gives you okay, what d type do you want to do the accumulation on, etc., etc. So all of those are sort of like abstracted away from the program essentially. um, so now essentially like uh, you can think of like going back to the let me see, where's the kernel. So so all of this kernel essentially like, which is about like 130 lines of code, which was using like the WMMA API, it like reduces down to like sort of, I guess it's like it's actually more code, but I think I actually add like bunch of sort of like cleaner abstractions. So I actually also show the PyTorch wrapper here. So, but it simplifies things so you can actually reason about it in sort of like higher level abstraction. So you have a gem op where you define your configuration for your d types, and what is your what is the d type for your accumulator, what does your epilogue op looks like as you're doing sort of the accumulation with like the like a standard MMA is, for example, like alpha times like AB plus B times C, etc. So you can essentially uh, um, think of the epilogue as like the as a final linear combination of the two operations. Um, um, but essentially, like like as I said, like this basically Cutlass started to click for me. And like now it becomes like sort of easier to like look into other other optimizations, which would be fairly hard if you're doing sort of raw indexing onto your kernel. So like I had heard about swizzling, like so I had seen these like colorful diagrams, or like but I had no idea like what those ideas meant. But essentially, like Cutlass, at least like the 2.0 provides you like essentially just like a single. Let me go back to, yeah. So like it basically just has an argument that you can provide directly to like what type of swizzling do you want on your kernel, as directly essentially just as an argument. And essentially like the piece I talked about in terms of like the double buffering or expanding that to sort of n buffer, like the pipelining is also provided as sort of an abstraction here. uh, yeah, so essentially like at this point, like uh, like when I was reading some of these like blog posts here and there, like I'll hear about like persistent kernel, swizzling, pipelining. Things started to sort of like make more sense to me. Um, but yeah, I think briefly we can. I wanted to cover swizzling later because I think it became more important for Hopper. But I guess like we can quickly cover it. Like the idea is essentially like what the way I understand is like when you're loading data, essentially you are bounded by sort of like these 32 memory banks. So essentially, like as you're going through your single buffer, you have these like theoretical essentially like cutoffs where you actually like the banks that will be used for the data copy will actually start to collide. So essentially, so for example, if you were looking at like 30, so yeah, this one actually makes things more easy. So essentially, like if you have like let's say 32 by n dimension tile, so you'll every 32 index will actually be mapped to the same memory bank. Uh, the and like the way you get around it is essentially you just like remap the indices along the dimension, so like your individual loads actually map to different memory banks. So essentially, like for example, here we just swap out the first and the second index on each of the rows. So essentially, like your now the thread zero will map to like bank zero, and thread one will map to bank one. But here, you essentially your T one will map to bank zero, and T zero will map to bank one. Um, um, and I guess like there's a bunch of different ways of like doing these layouts, and depends on like the dimensions of your tiles, etc. And but at the end of the day, essentially you're trying to do some sort of bit arithmetic on like sort of the uh, uh, on sort of the lower indices in your tiles. Um, but yeah, so essentially like the next sort of the extension of this was like as we talked about like double buffering and Cutlass. So like we can essentially like uh, utilize the abstraction that are already provided by Cutlass to essentially add like more stages to your pipeline. So started iterating with that's essentially like adding sort of more uh, uh, I guess like I didn't provide that listing here, but essentially like what you can do is you can just add like more number of stages in your gem operator in Cutlass. And the idea is you essentially just want to be overlapping as much as of your nodes and stores with your MMA instructions. Essentially, there's a bunch of cool like visualizations from like I think some Triton talks that were done during 2024-2025 period. So I think it goes this sort of drives home the idea. Like you wanna have fewer bubbles. You don't want to have your like memory operations be exposed in your lanes. You want to have essentially like GPU be computing as much as possible, and essentially like uh, always always have like your the loads and stores overlapped with your compute. Um, um, but like the idea, like what I really liked about like now getting to this point was like, okay, like I have this basic abstraction, and then I can just essentially like go through a bunch of these configurations and like see like what performance I can get for like different sizes, different matrix sizes. So like I basically just like went through like a bunch of like 2025 uh, different hyperparameters, essentially, where you just change your walk tile dimensions, your like thread tiles, and then essentially number of stages, etc. And then you can get essentially like at which size, like what is like, a good configurations for you to use. And like for me, like I use like n cross n dimension, but this could be interesting if you're essentially like have like a wider k dimension, for example, or like a wider m dimension, or it's like a longer m dimension, etc. These things can get fairly interesting. Um, so, but essentially, like once I ran through a bunch of these configurations, um, I was pretty surprised, like to actually like beat some of the Cubeless performance. Like my initial feeling was like some of the memory bound stuff here was like just like overusing registers to like get higher performance, like, but I was very skeptical of the results, but like I they were fairly consistent. And like when I was trying to look through like how I was doing the benchmarking, I was trying to sort of follow how Triton currently does it, like where they sort of it was sort of like adapted from like some of the Triton benchmarking code. So, um, but yeah, at this point, essentially, like I was able to like get performance that was beating Cubeless, but and like sort of magically, which was fairly interesting for me. I guess like yeah, it was fairly apparent. Like some of the standard like batch sizes were the closest to the PyTorch kernels, but some of the other ones were like a lot more faster. For example, um, yeah, I think like that was sort of the first part of like of my like I guess like starting to learn Cutlass. So like let me stop here. Like I don't know, Mark, if you have any more questions. Yeah.
No, I think people have been quite eager to hear more about Cutlass. I think we can keep going.
Okay, cool, sounds good. Okay, so yeah, so I guess like at this point, like let's go to part two. So essentially, like now as a sort of premise, like I'm like I'm not a I've written kernels in my life, and but most of them have been like sort of more like pointwise style kernels, like reductions, etc. But I'm not really a gem expert. So like I'll premise that. But essentially, like at this point, I was like, okay, like I can uh, now I understand like what Cutlass does, so I can just expand it to like iterate on Hopper. So this, I guess, like this was during like Thanksgiving, Christmas time. So I was like, sort of had some free time. So like started just adapting the same code to like work on Hopper. So, um, and I just use like the word. I think at that time it was like $1 per hour, so it was like fairly cheap. So I spent like probably $20-30 on Verda for to like Uh, iterate on this. But essentially, like, so I'll try to mostly cover the concepts here because I think like going to each individual kernel is probably not that useful because those are mostly just sort of abstractions that Cutlass already provides. But I think like this gives a good baseline to essentially understand like what are the key things to think about as you're sort of going from Ampere to Hopper to Blackwell. Um, so like the first thing I did was like actually like take the existing kernel and just like run it on SN90. Like it was good for again it was good for like some of the memory bound stuff, and I'm actually curious if somebody has like a good explanation for this. Uh, like but yeah, it was like bunch of like all of the like larger matrix sizes were actually like pretty bad. Um, so, but essentially, like this is like I think that there was already a previous talk on like Pranjal's post. So I think like that is actually like I would say like a lot more lower level. This is sort of more I would say like slightly conceptual. But yeah, to like get into Hopper, I guess like I read through a few sort of the architectural blog posts, which were useful to sort of understand like when people talked about like or like TMAs, like what did they mean, or like when people talked about essentially your thread block clusters and like sharing like shared memory across thread blocks, like what all of those conceptually meant. So like there's a good blog post from NVIDIA on like the Hopper architecture. So I think like some of this content is fairly like just like adapted from there, but I would like try to cover like four main things which are useful specifically from like gems perspective. So as we move from like Ampere to Hopper, the NVIDIA essentially provided like thread block cluster. So what you can do is essentially like originally you can own, you can't share like your share memory resources across your thread blocks, but like with Hopper you can essentially like operate at like these thread block cluster levels, so where you can actually share data across your thread blocks. And then I guess like the second one was like TMA, which arguably is one of the most important architectural change in Hopper. But the idea is essentially like as you're loading data from your global memory to your shared memory, you essentially don't have to go through your registers anymore. You can essentially directly load data from global to shared memory. And essentially there's also like I believe you can also do multicast from like your global memory to directly to the thread blocks in a specific cluster, in a specific thread block cluster. Um, uh, I guess like there were other things like where it was trying like it was trying to make sense like the things that basically you're taking like all of the asynchronous programming and like distributed system primitives and sort of lowering them all the way down to hardware really. So essentially it uh, like it, then so I think like NVIDIA added some primitives around like how barriers were more aware, were essentially data aware. So essentially they can they firstly they won't like spin, and also like they will sleep until like they have a specific amount of like bytes that they were expecting essentially. So and I guess like the last one was like as we sort of covered like you can essentially now that you can operate on like the thread block cluster level, you can essentially expand like the warp level MMA to like another level, another level deeper, another level higher up, which is essentially like your warp group level MMA instructions. So a bunch of these were added as part of Hopper. Um, and I guess like one of the reasons why I didn't use Cutlass 3.x or like whatever 3.4.x on my 4090 was I was not able to get the API to work on Ada and Ampere for some reason. So I struggled with that a lot, and then I eventually like gave up. So I stuck to Cutlass 2.x for like some of the original 4090 work, but then after I think like most of the I think you really need to be on like 3.x, I believe, like is for like Hopper work. But essentially, like the way I understand is like there was there were like major API changes that were done as part of Cutlass 3.x, so 3.x to essentially like uh, uh, make things so. Uh, uh, so the way I understand essentially like you uh, it's essentially just the abstraction was primarily like how you can build out your essentially your collectives algorithm, which is you take all of your MMA instructions and you up level them to like uh, like warp group level MMAs, and essentially they also provided some APIs to actually do essentially your fusions after you've done MMAs. For example, if you're doing the MMA plus a norm, you can actually fuse them directly in a Cutlass kernel. I believe like flash attentions you used upon use some of these like primitives in Cutlass when the original kernels came out. But essentially, like the I mean, this was adapted from like some of the NVIDIA documentation. So you can think about like the new API essentially just like had like a slightly hierarchical structure that sort of mapped uh, uh, in sort of you have this like higher level layer where you just define the gem up, and then you have some of these like sort of like your scheduling layer, like sort of pipelining layer, where you specify what would be your scheduling algorithms. Then the next thing is essentially you would have uh, your essentially like are you doing like collectives like are you doing MMA for example, and what are your tile dimensions for warp for threads, etc. Um, then there's like sort of the lower level primitive essentially like they map directly to your essentially tensor core. So like the lowest layer essentially like maps directly to your tensor core instructions. Um, uh, I guess like conceptually, like I can try to cover some of the concepts. Like so, Mark, I have a hard stop at like at 15, so I try to cover like uh, essentially like quickly go through the some of these. But like, what do you think? Like,
That's totally fine. So I would say maybe just do a like a fast best of, and then
Hmm.
maybe we could
Okay.
always like invite you back if you'd like to elaborate more. So please do whatever works.
Okay, that sounds good. Yes, sounds good. But I can sort of quickly go over like the types of algorithms that are useful to just sort of understand algorithms or sort of concepts that are useful to understand some of the gem optimizations. So let's quickly run through them. So like if you've heard the term warp specialization, I think that the term is sort of fairly self-explanatory, but the idea, like as we discussed before, like you're sort of landing in this like sort of distributed systems world. So you can think of pretty much your gem pipeline as like a producer consumer pattern. So your producer is producing data, and then your consumer essentially your compute you're doing like MMAs over it. So and I tried to sort of like get Claude to generate some of these visualizations, which was pretty nice. So essentially, like yeah, so you produce it like loading data, then you have a consumer warp that is operating on that data. While you're doing that, you essentially getting the next load, etc., etc. So some of this we already sort of did in the previous blog post as well. But essentially, this is where like things sort of big. You can think of this as like more sort of just like a producer consumer pattern, essentially. Um, Now, when we talk about like TMA warp specialized kernel, essentially like this is so let's get to that. As like the visualization, make it a little more clear. So essentially, now you essentially want to like now you can have essentially like your warps split up into your producer warps and consumer warps, and essentially you can do your async TMA loads on the producer warps. So essentially, like as you're loading data from tile A, tile B, you can do that on the producer warps, and you can essentially like uh, uh, run your consumer warps to do compute while you're loading data in your producer warps, essentially. But the same idea, yeah, I just expanded that into from like the 2 lane that we saw earlier to like 4 lanes, essentially. But the idea is essentially like uh, what TMA provides, essentially you can just load data directly from like global memory to shared memory directly. Um, uh, yeah, I guess like so. The next sort of optimization is like essentially like warp persistence, essentially. So the idea is like you essentially have uh, uh, Trying to remember. Let's actually go to the visualization. So essentially, uh, uh, you would want to split up uh, s- split up the work that you're doing along the I believe along the m dimension, and essentially like do it. Uh, I cannot actually recall what exactly was the process. So like, let me actually skip over that. Uh, uh, so I guess, yeah, let's go to ping pong. So now, uh, I guess like uh, uh, when we in the uh, in the consumer warps, essentially like what we end up doing is like we run the MMA instructions essentially like actually, yeah, now I remember. So essentially like in the warp specialized persistent kernels, you essentially splitting the data across multiple warps, and then you essentially combine it during the epilogue. So yes, you can split it along the m dimension and then combine it later in the epilogue. But what that does is essentially you would be waiting for that combine or essentially your gather operation that you need to do across the two. So you won't be using your tensor cores during that time. So essentially, like ping pong schedule just provides you of like essentially going. Uh, you can sort of use one warp at a time to use the to do the epilogue operation, while you can use the other warp to sort of to the do the MMA. So essentially, like here, what we're doing is like we have producer warps that are producing the data, and then we have consumer warps. Essentially, one does the epilogue, and then while this is doing the epilogue operation, the second warp can essentially start doing the MMA, and vice versa. Essentially, so this is, you can think of this like a three-stage pipeline. So your one warp is essentially one or two warps, I guess, like loading data, and then essentially your two warps are like ping ponging to actually do the compute plus epilogue back and forth. Now getting to like other scheduling algorithms. So it's actually like one of the things that we that happens when essentially um uh, like we want to be utilizing all of our essence at the same time, but sometimes what will happen is essentially you will have these like residual work that needs to get done, and like essentially your a bunch of your essence will sit idle. So for example, like let's say the work that you need to do is essentially like distributed across like nine different SMs. So in the last one is we only use like one of the SMs, and the three SMs just sit idle because the work always happens sort of like these like waves of like four SMs essentially. So we would want to sort of minimize a lot of this like SM sitting idle, and uh, the term that's used to sort of describe this is called like wave quantization. So because essentially the waves, you will have these like uh, idle sitting SMs, which like not doing anything. And I think Colfax has had a really good blog post on this like a while ago, where if you go from like if you change your like matrix dimensions, for example, you and if you look at your roof line, you'll see these like random dips in your roof line because of this wave quantization problem, essentially. And so there's a different ways to solve this. Like I mean, if you can think about it, like you can split the work into half. So essentially, like in the last wave, you will actually have two SMs utilized. So like that's basically the data parallel approach. But you can do better, essentially. So like. The problem is sort of like just reducing the amount of work, and now you're basically back to square one. if you remember like the blog post number one, we would want our compute to be doing as much work as possible. So essentially, like uh, if we have the work, that essentially means like we're not going to get like the good arithmetic intensity. Um, so the next idea here is essentially like instead of splitting the work essentially along the m dimension, you can split it along the reduction dimension, the k dimension. So and what you can essentially do is like what that allows you to do at least is like you can still use the same instructions, same tensor core instructions, while you sort of like use while you sort of have the work split in half, so you can get better utilization for like the last SL wave. Um, so so for yeah, we are at 150. So let me actually let me quickly go through, and I think like maybe we can like I can try to answer like questions later in the chat. So like stream K is essentially like the next extension of this. Like in the split K, we essentially split the work into like even chunks. Stream K, you essentially just like divide the work in such a way where you essentially like average out the works across the SM, so you get like even work over time on the SM. So like for example, like here, like the total work is let's say 10. So we're working on it so that like we allocate work to like in terms of like partial number of tiles, so you can actually get like averaged out work to be like 2.25 across, or I guess like the work was 9, we've been using 9, so like work would be like 2.25 distributed across the 4 SMs. um, there's a bunch of other like stream K optimization work, but I think like I'm not an expert, so I think like people should like definitely look at some of the Colfax research on this. Like, those blog posts were like actually pretty interesting, very hard to understand, but like I believe like very useful. And a lot of this like primitives around like stream K, split K are actually exposed in Cutlass directly as well. Uh, I guess we did cover swizzling earlier, but essentially, like again the same idea that essentially you need swizzling to avoid bank conflicts. Uh, so I guess like at this point, like I basically had like at least like a good basic understanding of like what are the main thing that you need to know about in terms of like gem optimizations. So I was able to sort of like go to uh, like write sort of like another auto tuning plan for like Hopper, where I basically like originally, if you remember, like in Ampere, we basically just did like the tile sizes and number of stages, but now you can essentially like expand that to like whether do you want to do split K, stream K, do you want to do what sort of swizzling pattern do you want, like all of those things you can essentially like uh, run. You can get to like I mean hundreds of thousands of different configuration if you go about it. Essentially, like I call it like the final YOLO auto tuning run, uh, which essentially like I was able to get to like 90% ish of the QBlast performance, and I'm assuming like so this was like PyTorch 2.9. I'm assuming this is probably better now, but I haven't like rerun this in a while. So like this is from like I believe from like November. So I believe it was 2.9 at the time. But like for most of the memory bound stuff, again, like we were able to beat the performance pretty easily. Uh, for like uh, for for 248 for 2048 it actually matched the PyTorch performance almost, and like for like a higher level ones we were still sort of lagging in performance. uh, but I think like it just required me to like iterate more on like some of the swizzling patterns, etc. And I think like this is where I think like experts come in. Like it was like my goal wasn't to like become an expert in like gem writing, but it was more about just like understand sort of the conceptual underpinnings mostly. Um, But I think yeah, that's basically what I had. Like I mean, I feel like I can like at least plug in like I can. So Cutlass has a bunch of examples which was super useful, and I like honestly like I was originally thinking about like iterating on the FP4 competition that happened. So like at least like some of the hopper work that I was doing was trying to sort of like I was trying to speed run through it to get to a point where I could like compete in that competition. But then I saw like people just writing like handcrafting PTX in their kernels, and I was like, okay, like I don't think I'm ready for this. So, but the TLDR is like I guess like there's a bunch of examples here, and depends on like if you have a consumer grade GPU, they also have like some of the GeForce kernels, for example. For example, like the next thing that I want to eventually try to get try to iterate on the NVFP4 kernels on like DGS Spark. I think there was some support lacking there. There were like, at least like some of 13.0 didn't have all of the things I needed. I think there was some work happening there, but I haven't checked in a while. So like I think like as sort of support for like DGS Spark get better, I want to like sort of iterate on NVFP4 as well. But yeah, these examples are great because this actually like I actually found these much later when I was iterating on the Hopper kernels, like, and then I was quickly able to sort of like understand like okay, what does the split kit looks like? I can just quickly run these like binaries to like see like the the performance characteristics of each of these configs. But yeah, I think that's all I had.
Cool. Thank you so much, Kapil. Always great to have you. You're more than welcome back. Yeah, and I hope everyone enjoys the rest of the weekend. Thank you, everyone.
Yes.